Ola, good afternoon. Bueno, imos ca presentación de Santiago, un pouco difícil despois do lunch, pero bueno. Vou empezar eu, que son Jesús Liñares, do grupo do Laboratorio de Materiales Cuánticos e Fotónica. Continuará Javier más, do IGFAE, e despois Tomás, Fernández, do Citius. Bueno, entonces, I'm going to present the activities of the Laboratory of Quantum Materials and Photonics Group from USC. It's more or less it's an experimental part, and then our research line correspond to the line 2, hardware for quantum communications, and two tasks, QKD, hardware for QKD in optical fibers, and also enabling technologies, integrated devices. Okay, then the primary aim is the development. It means theory, design, fabrication, optical characterization of photonic integrated circuits by ion exchange in glass. It means ion exchange glass chips. And for high-dimensional passive QKD in optical fibers. We use path and polarization optical modes. You can see a general integrated device in the image with synchronic directional couplers and also phase shifters, okay? Well, the question is that the ion exchange in glass is a simple and efficient technology because you can control the fabrication parameters very accurately, very precisely, okay? So it's a technology also, a platform, ion exchange in glass, highly compatible with optical fibers. And finally, it's a low-cost technology, okay? Well, we study three kinds of devices from an experimental point of view. Devices for passive measurements of high-dimensional QKD states, devices for passive generation of high-dimensional QKD states. High-dimensional means 4 or 8, dimension 4 or 8, okay? By using or by photon source, SPDC, spontaneous parametric down conversion, or even by using coherent states. It was a proposal by Marcos Curti, okay? Our primary aim is to use SPDC source, but integrated in the ion exchange glass chips. And finally, a third kind of devices are devices for passive compensation. It means to cancel the optical perturbations in the optical line. It's the plug and play QKD, okay? This is an image of our equipment for fabrication of selective ion exchange in glass. It's optical lithography. We have a deposition chamber, a photoresist spinner, a laser writing, an IonX oven, working around 300 and 500 Celsius degrees. We have a microphotolithography equipment. All this is only for proofs of concept because our equipment has some limitations, okay? But we can prove if the device is okay or not. Our first contribution was a paper entitled Quantum Projectors Implemented with Optical Directional Couplers in Ion Exchange Glasses. The primary result is that determination of empirical curves to obtain the fabrication parameters of a very wide family of synchronic directional couplers, and so, therefore, of many photonic integrated circuits, such as quantum projectors. A quantum projector is a device to measure quantum states. For instance, you can see, I don't know, you can see this point up and this point down is a projective measurement, okay? It's a projective measurement in an optical base. In this case, it's the Y base, but we can use another base, but not us, because the circuit can change the base in a random way, okay? And we can measure the QKD states in a random base, optical base. In this circuit, the important thing is the directional couplers, and we need a phase shifter, a phase gate, okay? A phase shifter. But there is another ion chain glass chips like this one that doesn't need phase shifters. This chip implement POVM projective measurements, okay? But there are many other devices, integrated devices, which doesn't need phase shifters. For instance, this is a passive generation of QKD states with SPDC. Our primary aim is to introduce this quantum source inside of our chip. It's an ongoing research project to integrate SPDC source in polarized ion chain glass bipoling. Okay. This is another example of integrated device to generate random QKD states. It's based in a proposal of Marcos Curti, but in this case with path modes, no polarization modes. Okay, we can use multi-core optical fibers, for example, and so on. For instance, we can implement chips for Bell stage measurement, for autocompensation, and so on. But the problem, our problem, was the phase shifters. So we propose these devices to implement phase gates with synchronic directional couplers, in particular abrupt directional couplers. We can see gradual directional couplers and abrupt directional couplers. And these abrupt directional couplers or this other kind of directional couplers can implement phase shifts. And these phase shifters are very robust. It means that small imperfections don't produce large errors. It's very important. These phase shifters are close to topological phase. Okay. This was the second contribution, and this is a quantum projector for dimension 4 when we use Q quartz, okay? And the measure is in a random base, optical base. We need eight paths, okay? And these results can be easily adapted to other platforms. For example, to silicon, which is highly compatible also with optical fibers. The third contribution was a chromatic study of our chips, because the wavelength is a very important parameter in these devices, okay? In particular, we study the short wavelength band between 700 and 900 nanometers. It can be interesting for QKD in short distance, of course, in optical fibers, or can be very interesting for free space QKD, this chromatic study, okay? And another activities are related with a proposal of a new protocol. It's a variant of the BBM 92 protocol, but the advantage is that it has intrinsic autocompensation. It means that the perturbation of the optical lines are cancelled in a natural way, okay? And it has all advantage of the MDI protocol. These are the 4 contributions in publications. Now we have sent to submission another works. This is an extension of our results to continuous variable. It's very interesting because the optical communication, standard optical communications, has many homodyne detection systems. Then we can use this kind of devices to generate QKD. And finally, another ARKIP work is a hybrid cryptography. It's related to my question to the Professor Marcos Luca Martini, okay? Because the submarine lines are very long, and our proposal is to introduce a hybrid a hybrid approach. It means that introduce additional physical security layers, of course classical additional physical security layers, because to insert in the submarine lines several trusty nodes is quite complicated from a technological point of view. And I finish this is a slide about our equipment to characterize our optical devices. Is the optical system working? This is a small image of the chips, glass chips. This is our SPDC source, quantum source. And this is the material which was acquired by the financial support of the Quantum Communications Program. Thank you very much.
So we continue immediately with the second presentation and then maybe have time for questions after that. Or if this takes a while, does someone want to ask a question now? Sure.
Thank you. Question, these optical chips, can you make them polarization independent? Yeah, independent of polarization. I come in with my light in this chip and beam splitters, whatever. This is polarization independent. You can design them. Okay, but not independent of a polarization.
Okay, then we'll continue with the next presentation by Javier.
Okay, so good afternoon. My name is Javier Mas. I belong to the IGFAE, Instituto Galego de Física de Altas Enerxías. And well, I'll be very brief. So my contribution to this project is quite small. So just to frame the work that we have been doing at the IGFAE, let me start by saying that I am a theoretical physicist working in quantum gravity. So it's something which sounds a bit scary and probably very far apart from this. From the side of what you're interested in, I would frame our work in the context of what's usually called quantum state transfer, which is something similar to quantum state teleportation, which is what you all have learned in standard textbooks, but it's not quite. It's more a kind of teleportation that happens in condensed matter systems instead of photonic systems. Yeah. So essentially, you think you have a lattice or a condensed matter system, a spin system. It has a Hamiltonian, and then you can insert a state, say at the end, and then the Hamiltonian will scramble the whole thing with time. At some moment, you will not recognize what you inserted in, but there's if the thing is correctly chosen, there will be a revival at some moment, and this revival will happen somewhere else. And this is the quantum state transfer. Yeah. So to be more concrete, so you see this circuit here is more or less what I've been saying. So there's a circuit, and then you insert psi on one end of the circuit. There's something going on in between, and then you recover this psi at the other end of the circuit. The circuit is a proxy for your solid or your condensed matter system. In our case, the kind of condensed matter system we have been working with has a name which probably you have never heard. It's called SYK Hamiltonian. It's a bunch of Majorana fermions. And it has some mysterious relation with the physics of black holes and wormholes. So in essence, this process of inserting the state at one end and recovering at the other end is dual in a sense to what happens when you plunge into a wormhole and you are ejected at the other side of the universe. And there's a way to bring this thing to a more rigorous this statement is to a more rigorous mathematical statement, which goes under the name of the ADS-CFT correspondence. You might have heard of it at some moment. Has something that boils down from string theory, and it proposes that this kind of revival should be seen in a quantum computer. So this is a difficult project. We have not achieved this quantum state transfer, this condensed matter teleportation. There are many groups. Google announced it at some moment, but it's very much cast under doubt. But this project has several steps that you have to fulfill. One of them is creating the initial state. You know, the initial state is sometimes the bottleneck of quantum computing. One of the bottlenecks that is usually ignored. So producing the initial state here is called the thermophile double of this Hamiltonian. It's just a name. It's a state that you can. It's well known in the textbooks. So to produce this state is a difficult thing, and this was the subject of the first part of our research. And then to study the stability of the dual geometry. So this concerning research. Also, I'm involved in other part of the project which has to do with equipment, and in particular, since I'm very much involved in education, and many of you know that I'm the coordinator of the master program. So we bought this equipment here, which is this 1-qubit quantum computer, which is based on NV Center. And this we use in the classes for demonstrations. Is the only, if they want, the only optoatomic setup that we have so far in the master. We hope to have more in the coming future. So, but we use this one qubit quantum computer for explaining things at the master, also for outreach. So I've used the money for having 2 PhD persons that have been involved in this research projects I've been talking about. And so we've published a couple of papers that, let me see if this goes or doesn't go. Well, if not, okay, here. So the first one is precisely the one that I commented upon, which is the fact that you have to prepare a state. It's worthwhile stating that this article had a spin-off. We realized after publishing that this method produces automatically the full spectrum of your Hamiltonian, and then we initiated a collaboration with CESGA, with Dani Faeldi, who's sitting there, and Mestre Lab, who are Alexandre, who is sitting upstairs. We initiated a collaboration to try to use this bonus track that this method produced to try to match NMR spectra. So we hope to continue this collaboration in the near future. So the second and third papers are more technical. They if you know the word floquet, has to do with the possibility of exciting periodically a system, periodically in time. So it's the same system, but with a periodic driving. This is more or less what I wanted to say. I think Tomás is coming next. Yeah. If there's any question or...
And we can take one question real quick.
Yeah.
Just one quick question, Javier. When you say preparing the state is the difficulty, is that the state that you're going to teleport or the state that is involved in the implementation of the Hamiltonian?
Is the state you inserted. Imagine you have 0, 0, 0, and you just insert a 1 qubit state in the first qubit, and then you wait. And this pops up at the end. It's the same as teleportation, but it's mediated by a lattice of things. It's not by a photon.
But does that mean that you can only teleport a particular state? So it's not a universal...
No. It's a generic state. I mean, you can insert any.
Okay.
No, it's
all right,
state.
Thanks.
Okay, and then we have the third talk by Tomás Fernández Pena. Go ahead.
Hello, thank you. I'm going to be very brief. I'm going to present the development we carried out in the CITIUS, in the Centro of Centro de Investigación en Tecnoloxías de Información of the USC. I'm going to change completely the subject. Now I'm going to talk, we work in software, and our point of view of the QPUs of quantum computing right now is quite similar to the one of the CITIUS. We think that the QPUs are going to be used like GPUs or FPGAs are used today into a computer system. So we have a classical computer, a classical supercomputer, and we have a quantum processing unit that can be collocated in the same node that the classical one, or distributed around a supercomputer, an IGPC system. So our line started with the study of the state of the art in quantum computing, in general, in distributed quantum computing, and in quantum intermediate languages and quantum compilers. Quantum intermediate languages are used by the compilers to translate, instead of translating directly for high-level languages to the assembler, quantum assembler. Quantum intermediate languages is a middle like this. Middle layer is about here. So the software is translated to these intermediate languages, and from these intermediate languages, another compiler translates to the specific language for the specific QPU. So we start studying the state of the art in quantum computing, distributed QC, and quantum intermediate languages, and we present 2 reviews about these topics. From these topics, we start to work in 3 lines. The first line is developing a new intermediate representation for distributed quantum computing that we call NetQueer. Queer, without the net, is a Microsoft standard. It's quantum intermediate representation developed by Microsoft for quantum computers. So we extend queer. We put the net in front of the Q, so we can use this intermediate representation with a distributed quantum computer. This intermediate representation is based on LLVM, so it's quite general. There are a lot of software supporting it. The second line is the integration of quantum computing as an heterogeneous devices. As I said, we think that the QPUs are going to be used like an accelerator. We have a code writing in a high-level language like C, C++, or Rust, or any one, and we define a kernel that is moved to a GPU or moved to a QPU. So we think that instead of reinventing the wheel, we propose to use the current standard for programming accelerators. And there are 2 standards. The most important one are OpenCL, POCL, and SYCL. This OpenCL is based in C, and SYCL is based in C++. OpenCL, let's say that OpenCL is low level and SYCL is high level. So we propose to extend these classical languages to include QPUs as accelerators. And the last line is the development of the simulator for distributed quantum computer that is called NetQ-MPI. MPI is the standard for programming distributed memory computers, and they are proposed from, I don't remember the name of the author, I don't remember the name. They are proposed of extending MPI to the quantum realm. So the proposal of QMPI is more theoretical than any other thing. Is only a proposed without implementation. So we propose a real implementation that right now works on simulators. This project, the PC3, allows us to contract 1 person for 2 years. The person now is working, Jorge, is set over there, and now is working at Técnica. Continue in the same line of the distributed quantum computing, but it's not exactly like that. And we have 2 PhD that we hope at least one to be presented next year. At least one. I'm looking for you. Yes, I'm looking to you. You have to present it next year. As the results were presented in 5 journals. One is the review of distributed quantum computing that was mentioned before for David at Técnica, what we prepare with people in Técnica, and what published in a very good journal that is free of 258 journals, so it's very high impact. The other journal was presented in the Future Generation Computer System was the presentation of NetQueer, that was an extension of Queer for distributed quantum computing. And in the Journal of Supercomputing, we present also a review for the intermediate representation. The InQuasm, that is an Inquire compiler to NetQuasm. NetQuasm is also a low-level programming for distributed quantum computer. And finally, we present the QP integration in OpenCL for heterogeneous programming. This is in journals, and in international conference, we present another survey, this time for quantum compilation process in the Europar 2024 conference. And the NetQMPI and SQL we present 1 month ago in the IEEE clusters in Edinburgh. Also, we make a presentation in the ECA this year. And I think that is all for me, from my part. Yes, this is all.
Does anyone have a question for Tomás?
Okay. I forgot to say that these last 2 posters we present in the cluster are presented like poster and are here. So if you want to know more details, you can ask.
Okay, perfect. We'll check that out and ask your questions there. Then thank the 3 speakers again, and we start with the next session.